Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, Vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. Section that tell us more about the types of cooling tower. One of the questions was specifically about the types of cooling towers. It was asked way back, probably 1 or 2 months back. So we are trying to address actually all the queries or all the requests that has been made on our videos. So today we are going to discuss about the types of cooling towers catering to the request of one of our subscribers who has commented on the earlier videos about video about cooling towers. So if you do not know the working principle of a cooling tower, just go and refer to the earlier video about cooling towers where I have discussed the working principle of a cooling tower. Today I am going to discuss about the types of cooling towers that are available in the industry and where and how they are used and what is the working principle of each of the individual type of cooling tower. So talking about cooling towers can be basically divided into several categories, mainly based on two types of categories we are going to discuss on. That is based on the type of air draft that is being used, we are going to classify the cooling towers, and based on the type of flow, we are going to classify the cooling towers. Apart from this, there is a type of shape classification, there is type of material classification, but these are the two main types that we generally classify cooling towers in. So talking about firstly the type of air draft, that is the type of airflow that is being used in the cooling tower. It can be classified into three basics, that is atmospheric cooling tower, natural cooling tower and mechanical draft cooling tower. So type of the air draft. So talking about atmospheric cooling tower, we are going to discuss about that. First let us classify atmospheric cooling tower, natural draft cooling tower, mechanical draft cooling tower. So mechanical draft cooling tower can be further divided into forced draft cooling tower and induced draft cooling tower. We're going to come to that, what is forced draft cooling tower, what is induced draft cooling tower. Now coming to the type of flow, it is basically two types of flow. If we classify the cooling towers, two types of flow are available, that is crossflow and counterflow. We are going to come on either of them. What are the advantages, what are the efficiencies of both the type of flows. So talking firstly about the type of draft and the first type, that is atmospheric cooling tower. So coming to atmospheric cooling tower. Atmospheric. So atmospheric cooling tower, it simply doesn't use any type of a draft or any type of a shape. It is basically a rectangular shaped structure wherein the water is being dropped from the top and the air is being allowed to flow from the bottom to the system. That is, it depends, atmospheric draft tower basically depends on the wind direction and the wind velocity. We do not tamper with the system. We do not fix a draft or we do not give a shape to a tower. We do not do anything. We allow a rectangular tower and a uniform distribution of water in it, and we allow the wind to hold its own direction of flow and with its own velocity. So it is basically a very cheap structure but not very efficient structure, because we do not know, it varies with the wind speed and direction. If the wind speed is slow, it will accordingly not move up, and in the midway, in somewhere between, the air will get stagnant because there is no draft or the push in the system. So atmospheric draft tower basically doesn't serve too much of the purpose, because it is mostly depending on the wind velocity, and it is not providing a draft or the mechanical force or any type of a shape to prevail or to create an advantage to the flow of air. So it may get stagnant in between. So that is the structure of an atmospheric draft tower. Now coming to an advanced version of the atmospheric draft tower is a natural draft tower. We have already given a structure to the natural draft tower. Natural draft tower. As the name suggests, this also doesn't have a mechanical push or a mechanical draft attached to it. It is basically a natural design of the tower, which is hyperbolic in shape. Like mostly if we show it in detail, like what is exactly the structure? The structure is somewhat like this. That is narrowing down from wide base narrowing down to the middle and then expanding at the top. Now I will give the reason for why the shape is like this, because many interviews in many Vivas in many semesters, it has been asked a number of times, why is the shape of the cooling tower as an hyperbolic cooling tower, particularly in natural draft one. So first of all, let's see that this hyperbolic shape in a natural draft cooling tower, first of all, since it is a very tall structure, in lug cooling towers we use it, where a lot of water is to be handled. So it is in lug systems, tall structures. When we require tall structures, when we require to handle a large quantity of water, we go for natural draft tower. Because what happens is, for supporting this tall structure, we need a wider base so that the area can be distributed and the load can be distributed, so that the pressure is not concentrated to a particular portion. So first of all, the base has to be widened. That's why we create a wide circular base. Secondly, why is the shape narrowing? Now you see, in a natural draft tower, as the name suggests, there is no forced draft, so the air is coming in at its natural pace. Now to increase that pace, as it goes up, it keeps on losing energy because there is a pressure drop as it is moving against gravity. So there is a pressure drop. To increase the speed in spite of that energy loss, we actually narrow down the scope, so that when we know that by Bernoulli's principle, V1A1 is equals to V2A2, that is velocity at the first point and area at the first point is equal into area at the first point is equals to velocity at the second point into area at the second point. By this principle, we see that A2 is lesser than A1. So V2 is going to be greater than V1. That is, velocity is going to increase. To increase the inherent velocity of the incoming air, the shape of the cooling tower is narrowed down so that it gets increased in the middle. Now many would ask, then why is it not like this? Why is it not like this? That is completely narrowed down structure till the end. Why is it again widening at the end? So what happens is, at the end, when the water vapors come out, that is, the air saturated with water vapor comes out, we need a proper dispersion of that air into the atmospheric air. That is, the proper mixing is required. To increase that dispersion, to increase the dispersion coefficient, to increase the dispersion, or to allow proper mixing, we should have a wider mouth open so that it can interact with the atmospheric air, so that it can mix up well. That's why it is in the middle, it is narrowing down, and then again at the end it is widening up to allow the easy mixing of the air from the cooling tower with the atmospheric air. Now in the natural draft, we are seeing the energy required is less because there is no installation of pump or no installation of fan to allow the flow of air. So the operating cost, the maintenance cost of those fans and the fixed cost is almost negligible. There is no requirement of that. Moreover, in tall installation towers, we require more horse pump if we give a mechanical draft, which is not required here, because in large installations we can just keep the shape like this and we can keep a natural draft system that is mostly followed in the industry. So natural draft is a go-go technology, and moreover the pressure drop is also less due to this hyperbolic shape. As I've already explained, it is increasing the velocity. So we are giving a natural draft to the system and maintaining a structure which enhances this flow of air and allows the natural draft to prevail. So natural draft is a go-go technology when you are installing for large water quantity, tall structures, lugs, that is industrial water. When you need a large cooling tower, natural draft can be preferred, because when you go for mechanical draft for a huge tall tower, you need a very good horsepower or very high amount of operating cost, regular horsepower. So in that case, we can prefer natural draft. Now coming to mechanical draft. The mechanical draft can be further divided into the forced draft. Now what is a forced draft? Supposedly this is my cooling tower. Forced draft is actually forcing the air in through a forced draft fan. You will often come to know about this as the FD fan. In the industry, in the cooling tower, we use FD fan. That is the forced draft fan. What it does is it sucks in the air. It sucks in the air from the ambience and it pushes the air which comes in contact to the water that is falling. And it allows the air to come in contact with the water. Now, what is that? What are the advantages of forced draft over induced draft? We will come to induced draft as well. So if we parallelly draw the induced draft as well, to just pull out a comparison, induced draft is nothing but the same draft system is fitted at the top. That is ID fan, induced draft fan is fitted at the top of the tower to pull out the water from the tower. So what is the difference? This is the FD fan, this is the ID fan. We are seeing one is pulling or sucking in the air from the system, one is sucking in the air from the atmosphere and pushing it in the system. So the advantage of forced draft over induced draft is we are seeing that as the air is going in with a thrust in a forced draft system, so what happens is it gains an additional amount of energy which is hence very utilizable when it comes in contact with water. That is, it gains an additional amount of velocity which is further converted into pressure energy, which is hence allowing a better interaction with the air-water in between the air-water system. So what happens is forced draft FD, first advantage is additional energy at the entry. Moreover, since the fan is fitted at the bottom, it can withstand, it doesn't get accustomed or it doesn't feel that much vibration, whereas the fan fitted at the top can feel a lot of vibration. Since it is grounded, the ground itself absorbs a lot of vibration in the system. When such a big system is installed, there are expected vibrations. So a FD fan actually can have a longer lifeline than an ID fan, because the vibrations are quite less in an FD fan. So vibrations are less. Now coming to the disadvantage. Since it is a forced draft system, what happens is it pushes the air to some extent. So it may happen so that the air will lose energy in the midway because there is no sucking or no pulling force from outside. So it may happen so that in midway it becomes a natural draft system that is rising on its own. So we have to calculate the amount of power that is actually required by a forced draft. So forced draft obviously would require a higher amount of power than an induced draft, because you need to push the air to ensure that it reaches the top of the tower, which is a difficult task again. Moreover, what happens is the big problem with the forced draft fan or forced draft system is the recirculation of the hot and humid air. That is, whatever air is getting out of the system that is hot, humid, that is, it is carrying water vapor, it is already saturated water vapor, and it is already very hot as it has heat exchange with the incoming hot water and has cooled the water in the process. So this air has a tendency of being recirculated back through this fan into the system. Because the forced draft, what it is doing is, this air is going out as hot and humid air from the top of the tower. What it is doing is, forced draft is trying to suck in the ambient air and push it in the system. So there is a tendency of sucking in back the air that is coming from the top of the system, which is a big disadvantage in this case, because we do not want that. We do not want the water to come in contact with, again, the hot and humid air that has exited out. So that's a big problem associated with forced draft fan, which is hence not a problem with induced draft fan. Induced draft fan basically sucks in the air from the system, so it has no chances of recirculation. That is, it pulls out the air and it releases it to the atmosphere. So there is no chances that it may go back into the system. There are no chances of the recirculation. Moreover, the recirculation is very much dependent in the forced draft. Induced draft, there is no chance of recirculation because we are pulling out the air. We are not feeding it back into the system. Whereas in the forced draft, the recirculation completely depends upon the wind speed. If the wind speed is high, it will carry that hot and humid air away from the entry of the FD fan. If the wind speed is low, that air may again settle back into the system and may again be pushed off by the FD fan into the system. So that's a very big disadvantage in terms of the push of air. So forced draft has its own advantages, but it has also got some disadvantages. Induced draft power required is less, there is no chance of recirculation. So in general, the industry mostly prefers induced draft rather than post draft systems. In terms of operating cost, in terms of recirculation, if you say, the only problem with induced draft is the additional vibrational energy that it faces. It often causes the maintenance of the ID fan a little hectic. So moreover, ID fan is difficult to reach as it is at the top of the tower, so its maintenance is a big issue. Maintenance for ID fan is a big issue because that needs to be maintained over time because of high vibration. Moreover, the accessibility becomes a problem in an ID fan. So having said the type of drafts, now coming to the type of coming to the type of flow. Two types of flow, basically, as we have already mentioned, crossflow and counterflow. So now let's draw them simultaneously. Supposedly this is the water incoming through the system, and this is the air that is encountering the incoming water. This is crossflow. And what is counterflow? The water incoming the system and the air moving parallel to the water in the opposite direction, parallel to the water in the opposite direction. This is air, this is water, and this is crossflow, perpendicular to the water flow. That is, this is air, and this is water. So this is crossflow, this is counterflow. Now, as you have already seen that in a counterflow and a crossflow system, basic difference what occurs is, in a counterflow, the driving force is much more higher, or I would say rather much more optimized, to be very on the topic, or very honest. Because what happens is, if you see, this is dry air, what is incoming in the system is a dry air, and at this point of time the water is the coldest. Because it has already cooled down to a great extent. When it came from the top, it went cooling, and the coolest water is available here. So if I take an example, supposedly my temperature here is around 25 degrees Celsius and my incoming air is around supposedly 21 degrees Celsius. So the CP heat transfer, that is the specific heat transfer, is not that dominating, but remember, the incoming air is a dry air, so the evaporative heat transfer is high. That is, a part of the water will be removed as vapor and the remaining part will give the latent heat and itself will get cooled in the process. Now, as the air goes up, it becomes humid, that is, it sucks in the water, and when it reaches the top, it is almost filled up with water, so there is no evaporative heat transfer. But when it reaches at the top, it supposedly has a temperature of 40 degrees Celsius, I'm telling, and the water that is incoming is having a temperature of 80 degrees Celsius. So there is a prevalent amount of specific heat transfer. So at the bottom, the optimized heat transfer mainly is dominated by the evaporative heat transfer, and at the top, when the evaporative heat transfer is not possible, the humid air coming in contact with the hot water is basically undergoing specific heat transfer. So it is an optimized process where the driving force is always remaining maximum in some of the other case. One is evaporative heat transfer driving force is maximum, here specific heat transfer driving force is maximum. So this is an advantage of a counter current over cross current. Another advantage of counter current over cross current is the cross current water spraying is basically done from a hot basin. Okay? And what happens is, it's an open system. So what happens is, when we transfer this water through louvers or allow the entry of air, what happens is, this is difficult to maintain, as algae growth is very much predominant in case of crossflow, and in counterflow the allowance of sunlight is very low through the louvers, and that's why the algae growth is also very less in counterflow than in crossflow. Moreover, when you do the maintenance, you need to call high professionals to do the maintenance of a cross-flow system, because there are a lot of integrated parts. You need to open up those and clean those. So the maintenance is a very, very difficult task in case of cross-flow system, whereas for a counterflow, the maintenance doesn't become that big an issue. So a lot of factors is there. Moreover, what happens is in a cross-flow system, if you see the air is being fed in, so what happens is it comes in contact with the water. And what happens is, when it goes out of the top of the system, there is a chance that it will again come back as a part of the cross flow. So there is circulation, the hot and humid air coming back into the system. Whereas for counter current, there is a very less chance, because counter current air is fed from the bottom and the air is exiting from the top. So there is a very less chance to for the top air to come back at the bottom to be fed again. Whereas for cross flow, there's a prevalent chance, because we are feeding it here, it is exiting from here, and it can easily come back here because it is fed in multiple stages. So in cross flow, there is a prevalent chance of recirculation, whereas in counter flow, since it is fed from the bottom and released from the top, there is a very less chance for recirculation. And there are several other factors to cross flow and counter flow, but these are the basic factors. So they have their own usages. One more interesting thing is, cross-flow obviously doesn't require that much energy since it is multi-fed, and also it is perpendicular system, so the pump horsepower requirement is very less in cross-flow than in counter-flow. You need a higher horsepower. So this is the disadvantage of counter-flow. So wherever your pump requirement is less, that is, you cannot provide that much power, you will prefer cross-flow. Whenever you don't want the algae growth to become headache, whenever you want a high driving force or a tall tower, you want extra advantages, lucrative advantages of counterflow, you don't want recirculation, you will use a counterflow. So power requirement wise, if you see crossflow is advantageous. If you see driving force wise, if you see recirculation wise, if you see maintenance wise, counterflow is easier to handle. So there are multiple factors associated with it. You are going to decide according to the need of the hour. Having said that, we conclude on today's topic, that is types of cooling tower. Hope it helps, particularly the one who has asked the question. So thank you once again. If you liked our video, like it, share it with others, subscribe to our channel. That's it for today.